All right, so definition. A be a matrix. And X equals, usually the vectors are denoted this way. So x1 down to xn. I would just write down be such that A times X makes sense, which means that their dimensions agree such that you can multiply that matrix by X. X transpose, when you see this sign on X, that means transpose. So that vector, when you transpose it, it becomes the row. So transposition turns a vector column into a row and turns a row into a column. So the expected value of the vector X is nothing but a vector that consists of the expected values of the component. So you want to find the expected value of the vector, then you find the expected value of each of the components, and you form the vector that you get from there. And if you want to find the expected value of A times X, that's nothing but A times the vector expected value of X. This is a vector. When you take the expected value of X, that's what you got there, vector. So you can switch A and the expected value. That's what it is, right? So the covariance of X, covariance matrix of X, expected value of X minus the mean of X transpose, because this is a vector, you transpose that vector, then you multiply by X minus the mean of X. See that this is the same as so, but my new notation is supposed Otherwise, if you transpose on the other side, you get a number, not a vector. Now, note that x transpose is actually, this is x, which is vector x1 down to xn. And x transpose is x1 xn. So when you're multiplying x by x transpose, this is actually what you're doing. And for those of you who had linear algebra, you know how to multiply matrices, right? How do we multiply? Row times column, right? But each of the rows is only one entry, and each of the columns is only one. So this ends up being an n by n matrix, right? So x transpose is actually an n by n matrix. So you're going to have x1, x1, then x1, x2, x1, xn, right? And then down x2, x1, down to xn, x1, xn, xn. So it's this matrix. And you're taking the expected value of that matrix, which is go inside there, take the expected value of each of the positions and make the matrix out of that. X transpose is actually therefore expected value of x1, x1, expected value of x1, x2, expected value of x1, xn, down to expected value of xn, x1. So that's how you take the expected value of a matrix. You take the expected value of each of the entries and you form the matrix that you get out of that. So when you compute that, what you get in the end here, you understand expected value of x transpose minus mu prime. This is actually a matrix. So what you get out of here is not a number, it is a matrix, an n by n matrix. That matrix is called the variance covariance matrix of the vector x. So the matrix that you get here is what we call variance covariance matrix of the random vector x. Why variance covariance matrix? Because in that matrix, along the diagonal, when you take expected value on the diagonal, you have expected value of x1, x1, expected value of x2, x2, expected value all the way down to expected value of xn, xn. And then minus, this is the mu square of each of them. So when you subtract this, along the diagonal, what you get is the variances of the random variables x1, x2 down to xn on the diagonal. And off diagonal, you will have a symmetry. The entries off diagonal are same if you reflect them with respect to the diagonal. And they will be equal to the covariances of the vector of the variables xi, xj. So at the position here, what you will get will be the covariance of x1, xn. Opposite to it there, you have the covariance of x1, xn. So all the entries of that matrix will be covariances, and along the diagonal you have variances. That's why it's called the variance covariance matrix of X. And now if you have a linear combination of those vectors, that matrix will be very helpful in finding the variance of any linear combination of those vectors. So that's the first object that you need to keep in mind when you're dealing with the vector x. Now, if we define y equals a times x as written here, then the covariance matrix of y is what that's going to be a times covariance matrix of x times A transpose. So if I'm looking for the covariance matrix of a vector that is a linear transformation of x, I don't need to take the formula of the distributions and start computing anything. All I need to do is transpose the matrix, multiply on the left, multiply on the right, and I have the covariance matrix of that. That avoids you having to do all the integrals and the sums and all the things that you had to do to find the mean and the variance. All you have to do is multiply these things and you have your answer. So that's variance, covariance of A times X. The proof is not hard, but I'm not going to be asking you to do that, so I'm not going to spend time proving that. For that same guy, the expected value of a sum of AI, xi. This is a particular linear combination when you just take one of the vectors, you multiply by a constant, and you just have one line, right? So this is not a vector, it's one number that is sum of AI xi. I from 1 to n. That's an example of that. And an application of this would tell you that the answer is sum I from 1 through n AI expected value of xi. That's an application of the original formula we have on the top here. This. And we will look for the variance, covariance. So let's say I call this thing T. If I call that thing T, so the variance of T will be what? If I want to use this formula here, what do I get? In this case, A and A transpose are just these. So that will be A and A transpose will be A1 down to AN. And the transposition A1, AN. When you put that around this matrix, what you get is a quadratic form, right? So you just use the formula of a quadratic form to say that this is actually just double sum of AI, AG, then covariance of XI, XJ. AIHA, yes. And the sum is over all INJ. That's why it's double sum. Generally, you would say the covariance of sum of AI's XI, sum of BJ, well, you don't have to be X anyway, so Y. X, started with X, that will be equal to the sum of the I, J, and then covariance of XI, XJ. So these are all applications of the formula we have on top here and this one. When instead of y being a vector, you have y being a scalar, because this is the case of a scalar. Let's take an example here. Example inside the example. Assume x1, xn are uncorrelated. I'm not going all the way to independent, uncorrelated random variables. With variances sigma square 1 down to sigma square n. Questions 1. Variance. Find the variance covariance matrix. Of x equals x1 to xn transpose. If I ask you that as the first question, then you would say, okay, the text of the problem says that the random variables are uncorrelated. What does that mean? Huh? Can't hear anybody. What does it mean that the random variables are uncorrelated?
Right. The correlation.
The correlation of any two of them is 0. So we have x1, xi, xj. Covariance of that equals 0. I not equal to j. So when I is not equal to j, the covariance is 0. So covariance matrix is equal to we know this notation. That means the matrix that has diagonal sigma of square 1, sigma all the way down to sigma square n, and everything else is 0. So find mean and variance of x bar, which is equal to 1 over n x1 plus down to xn. So find the mean and variance of x bar. What we call x bar is what we call in statistics the sample mean. When I take a sample from this data, what is the distribution? What is the value of the mean of that sample? It's the average of all the observations. You add them all, you divide by the total number of observations that you have. You call that the sample mean. And here I'm asking you to find the mean and the variance of the sample mean. That's the question. And so if I want to apply the lecture that we just had, this is what is going to happen. I'm going to say that x bar is 1 over n x1 plus 1 over n x2 down to 1 over n xn, which is nothing but 1 over n times x1 down to xn. And this is a times x1 down to xn, where a is equal to the matrix 1 over n, 1 over n. Therefore, expected value of x bar is equal to a expected value of x. Let's see here. Second, let me add here the means. Okay. They have means mu1 to mu_n. I'm completely wrong now, but that's what it is. So here, that's going to be 1 over n times mu1 down to mu_n, which is 1 over n mu1 plus 1 over n mu_n. So the expected value of x bar is 1 over n mu1 plus down to mu_n. So in the case when mu1 equal mu2 equal all the way to mu_n equal mu, you have expected value of x bar equal n times mu over n equal mu. In this case, we will get to that later on in this class. We say that x bar is an unbiased estimator of mu. So we say that x bar is an unbiased estimator of the mean mu because the expected value of x bar is equal to that mean. Now, what about the variance? I asked for the mean and the variance. So what is the variance? Variance of x bar. The formula says that it is sum over all i's and j, I from 1 through n, j from 1 through n, ai, aj, or variance of xi, xj. Right? But the covariance of xi, xj is equal to 0 unless I is equal to j, right? So anything where I is not equal to 0 to j is going to be 0 except when I is equal to j going from 1 through n. So that is going to be sum I from 1 through n ai squared, because when I equals j, it becomes ai squared, and then variance of xi, because the covariance of xi is the variance of xi. And ai in this problem is 1 over n. ai is 1 over n, so that is 1 over n squared sum I from 1 through n variance of xi in this problem. So that's how you would find the variance of x bar. Now when, that's the next special case that is usually studied, when all those variables have the same variance, when variance of xi are all equal to sigma squared, all of them, then that lets you to have that the variance of x bar is equal to 1 over n squared, and then sum I from 1 through n sigma squared. And because it's the same sigma, it becomes sigma squared over n. That's why you will have later on the famous formula that the variance, that the sample variance decreases when you increase the sample size. If you want to be more precise with your estimation, you increase the sample size. You get more people involved in the study. You will have in the study. You will have more accurate results. That's what it means. So that's what the sample size is for. So based on this, theoretically, when you're doing a study, a survey, the more people you put in the study, the better the result that you're going to get. Because n is the number of people that you're getting in there. You're getting observations from people, actually. And as n goes to infinity, the larger n, the smaller the variance goes to 0. And what does the variance represent actually in your study? It represents by how much you can be, your estimator can be off from the true value that you're looking for. If let's say we want to have elections in this country and I want to estimate how many people will vote for me as usual, and I go out there and start slating people and asking questions, do you think that during this election you can vote for this person? And then you collect all the information. The larger the population that I'm using, the smaller the error that I can have on estimating that. If I end up asking everybody, what should be my error? 0, because I know what everybody's going to say, right? Which is the ideal case, but in reality, the population is so large that you can never ask everybody and have the answers before you finish the study, which is the reason why often when you see a statistician watching the news is always pissed off, because those guys forget to tell you that whatever they're projecting there is not sure. There is a margin of error that they often shut up about. Margin of error, 5%. 5% of the time I can be wrong in this thing that I'm saying. And 5%, that's a lot. All right, so those are just comments ahead of time. When we get there, you understand what I'm talking about. It's all part of this class, but later on. So is this clear what I've done here? Everybody understands it? All right. So let's say there's another guy here actually. Question 3 here. And I can let you guys think about this. Usually when we use x bar in statistics, it has a friend that always comes with it. We call it s squared. So find the mean of s squared. What is that? It is 1 over n minus 1. Sum I from 1 through n xi minus x bar squared. What do you think? How would I find the expected value of that? So, 2 minutes to think. And I claim it's the same topic we are working on. It's an application of those same formulas that we just applied here. So how would you?
Expectation of central. Expectation of central.
Yes, the same idea. Well, how would you?
These will be variances.
So you are claiming that expected value of s squared, of course, we leave out that 1 over n minus 1. We'll leave out sum I from 1 through n, and then we put in here expected value of xi minus x bar squared. How you do next? Variance of. I want you to apply the formula. There are many ways to do that, but I want you to apply the formula that we had out here. How would you? All right, let's forget about that. What do you want to do here? Yes, I said let's forget about the method I want to apply. What would you apply to all the way to the end? This. Oh, be careful. This is x bar, not mu. This is a random variable. That's a random variable. How do you find the expected value of this?
Xi minus x bar and xi minus x bar.
Cross multiply.
Yeah.
Right. So you need to cross multiply the thing there. Okay, I agree with you. So let's do that. So it's 1 over n minus 1. So from 1 through n. When you open the parentheses here, you're going to have expected value of xi squared minus 2xi x bar plus x bar squared. What next?
You move the expected value linearly.
Correct. We move the expected value linearly inside, and that becomes expected value of s squared equals 1 over n minus 1 sum I from 1 through n expected value of xi squared minus 2 expected value of xi x bar expected value of x bar squared. Okay, what's next?
Yeah. Distribute the sum.
Okay, we can do that. It's not a problem. 1 with n minus 1. So this sum is going to be now sum I from 1 through n. Expected value of xi squared. Okay. Minus 2. Sum I from 1 through n. Expected value of xi x bar. Do you see something funny that I can see? What's expected value of x bar squared? We did this, that's okay, that's fine. There's something funny there that you can see. Something that will make this simpler.
Why is there the sum at the,
What's that?
why don't you have the sum at the last,
Because I actually still keep them together.
those are still together?
I want to. I'm just telling you what I actually want you to see. All right, so I just gave the answer to my question. What can you see here that will make this computation simple? It's way back. Yes, no, not that far. It's very simple between this thing and that thing.
Expected value of x bar squared doesn't depend on I.
Yes, so that's also a good thing to see. So this is going to be n times the same thing because it doesn't depend on I. Good to see. But that's not what I actually wanted you to see. But it is good. We also need that. So I can already use that. I can already say, okay, that's 1 over n minus 1.
Value of x by mu. We supposed
Don't go there yet. What I need you to see is before that. Okay. Look carefully. Again, I say it's between this guy and that guy. These two things have something in common that you can see. What is actually x bar?
Estimator.
No. What's the formula? Sum of xi divided by n. And what is this? What's the game that we play with the expected value and the sums?
We can take expectation out.
Because No, if you say that, that would be kind of the wrong way to say it if the problem changes. What you're doing is you're bringing the sum inside the expected value. Because you can't separate the expected value from the x bar that is already here. So you're bringing inside expected value, bring inside that sum. And once you bring that sum in, that becomes n times x bar. So actually this whole thing is actually n x bar squared. Am I making sense? So right here, this piece is actually expected value of sum of xi's times x bar, right? Just by taking the sum inside the expected value. And that x bar is still inside the expected value, so there's no mistake, right? Does everybody agree with that? Are we on the same page? All right. And once I write it like this, I can see that this is nx bar. So the whole thing that you have there, expected value, is actually nothing but expected value of nx bar squared, which is nothing but n expected value of x bar squared, which is exactly the same quantity that is here. So from the very beginning, you could avoid all the calculations because this thing is equal to twice. This thing is twice common. So your computation here will lead you to expected value of s squared. And I'm hoping that we understood now what is the issue here and how to get rid of that thing. This is coming back later in more complicated setup. So please try to understand now what we do. N minus 1. And this one here, it's sum I from 1 through n. The expected value of xi squared is actually sigma square I plus mu I squared, right? Because the variance is equal to the square of the expected value of the square minus the square of the mean. So this here is sigma square I plus mu I squared. So that's sigma square I plus mu I squared minus n expected value of x bar squared. Now, how do we find the expected value of x bar squared? I just wrote the answer. Expected value of the square is the variance plus square of the mean. Right? That's what you write here. So, and we already computed the variance of x bar. So that's 1 over n minus 1 sum I from 1 through n sigma I squared plus mu I squared minus n, and the variance, that's going to be variance of x bar plus expected value of x bar squared. All right? Because by definition, the expected value of the square, this is all inside, is equal to the variance plus the expected value of the square. The variance of X bar, we computed it on the previous page as 1 over n squared sum of variances. The variance, we got that to be 1 over n squared sum from 1 through n sigma square I. That's what we got here, right? And then plus, what's the expected value of X bar? That's this. The special case when they are all equal, it's mu, but what we got as expected value was the sum of the means, mu1 plus mu n squared. Now, if you're doing this, you would see that here the n squared cancel, the n cancels with the n squared, and you got 1. What's that? In the special case when mu1 equals mu2 and they are all equal to mu n or mu and sigma squared is same for all of them. If they all have the same sigma squared and the means are equal, then this will turn into, so it's not all the time that it's equal to what you think is equal to. It's under those conditions that you have the equality that we talked about, right? If they are all equal, then this is n sigma squared plus n mu squared. This first part, because they are all same, minus now here this is n sigma squared, so that's 1 over n. Yes, you want to see? All right, sorry. So here in this one, when they are all equal, that is again sigma squared for all of them times n, and then you had 1 over n squared. So it becomes sigma squared over n. And this one, because all the means are equal, that's going to be n squared times mu squared over n squared, which is just going to be mu squared. And so you can see the n mu squared cancels with the n mu squared here. And that's the only reason why we are ending up with this sigma squared n sigma squared 1 over n minus 1 and then n minus 1 sigma squared, which is equal to sigma squared. And in this proof, you can see that if these two conditions are not satisfied, you're not getting that. So you shouldn't always say that the sample variance is the expected the value of the sample of the variance. I mean that the expected value of the sample variance is equal to the variance, not always true. It's true here because all of that is true and all of this is true. remove those assumptions, you don't have it. The second thing is here we are assuming that the variables are uncorrelated. Remove that assumption and you don't have this result. And I'm especially talking to those who are dealing with statistics and in their research and doing some estimation problems. So when your data is not independent, you don't get to say that you're estimating the variance of a population using S squared. You don't have that luxury. Any question? All right, so if there is no question, then we start doing the easy things that we'll be using all of this. We talked about these two guys before. Start by them again. So let's say we have x1, xn.
Hey, Dr. Longo.
Yes.
Katie Ann Wheeler got kicked out by accident. She needs back into the class.
Oh, couldn't see that. Thank you. So if we have x1 up to xni independent, and identically distributed random variables, from the Bernoulli distribution. Okay. If we have independent and identically distributed random variable x1 all the way up to xn from the Bernoulli distribution, then 1 y equals 1 over n x1 plus xn is a non-biased estimator of P, which is the probability of success. That the expected value of y equals 1 over n, expected value of x1. And because they are all from the Bernoulli, let's say have here with parameter p. Okay. You know the distribution, the Bernoulli distribution has one parameter p, which is the probability of success, and the expected value of x is equal to p. We proved that earlier. So that'll be 1 over n, p plus p all the way down to p n times that's p, which shows that this is an unbiased estimator of p, which is the probability of success. So variance of y is equal to 1 over n squared. Based on the formulas that we had today, the variance is 1 over n squared sum of variance of xi from 1 through n. And we have proved already that the variance of this thing is p times 1 minus p, right? So that's 1 over n squared times n variance of x1, because they all have the same variance, that is equal to p times 1 minus p over n. So this is the variance of that estimator. Random variable z equals x1 plus down to xn is binomial. Random variable. Parameters. Yeah. So the random variable z equal the sum of those independent and identically distributed Bernoulli random variables is the binomial random variable. We talked about the binomial random variable earlier, right? So here, of course, the expected value of z equals n times p, because it's expected value of x1 plus expected value of x2 plus down to xn. They are all same equal to p, so it's n times p. And that's why the expected value of the binomial is n times p. But now if you go look at the formula of the binomial distribution and you try to prove this thing using the formula, it will take you a lot more work to find that the expected value is n times p. Do you remember the formula for the probabilities in the binomial? It says probability that x equal k equals choose k out of n times p to the k 1 minus p to the n minus k. And you want to multiply this thing by k and add k from 0 to n. And find a way to add that and show that that sum is equal to n times p. Okay. But here, after this thing that we have done, we know that that sum is binomial. The expected value is the sum of the expected value, which is this one plus that one, and they are all equal. The expected value of each of them is p, so it's p times n. That's the answer, and I don't have to suffer through this sum. Am I making sense? And based on what we just found here as well, the variance, and I don't need to suffer through the sum with the square to get the variance. The variance of z still can be obtained from here. We got that it's n times p times 1 minus p, because we just need to multiply this thing by n squared. So the expected value of the binomial is np, and the variance is n times p times 1 minus p, and I don't need to compute the sums to get it. Any questions? Now let's have an application of something that we wrote earlier. How do I get the moment generating function? How do I get the moment generating function of D? We have computed the moment generating function of the Bernoulli, right? It's just two values, right? 0 and 1. So if I want to find the moment generating function of the binomial, look at what you should be doing, right? You take this as probability times e to the t times the value, right? And you add that over k from 0 to infinity. That's the definition the good student will use. But now, if you have done what we did today, and you know that this sum is the binomial random variable, and you know that the random variables are independent, this is how you're going to answer this question. You would say the moment generating function of x1. How do I get it? So m x1 of t equals what? X1 is a Bernoulli random variable. What's the MGR?
P plus 1 minus
P times?
P plus 1 minus P times.
No, go slowly with the definition. Not, I know the answer you're giving is correct, but how do I get it?
P times e to the 0.
P times e to the 0 t plus 1 minus p times e to the
T.
1 times t. Yeah. That's the definition of the moment generating function. E to the expected value of e to the tx. And x has only two values, 0 and 1, with probabilities p and 1 minus p. That is why the answer is p plus 1 minus p e to the t. So that's the moment generating function of x1. And then the moment generating function z of t equals what? Expected value of e to the t z. This is equal to expected value of e to the t x1 plus t x2 plus t xn. And because the random variables are independent, the expected value of this product is equal to the product of expected value. That's expected value of e to the tx1 times expected value of e to the tx2 times expected value of e to the txn, which is equal, identical. They have the same distribution. X1, X2, all the way down to Xn have the same distribution. So these moment generating functions are same. So that is just equal to expected value of e to the tx1 raised to the power n, because it's the same function multiplied n times. And the expected value of e to the tx1 is what we just wrote here. So that is p plus 1 minus p e to the t raised to the power n. So that is the moment generating function of the binomial, and I don't need any sums to get it. Questions? Any questions? My good old silence is back. All right. Exercise. X of t equals 2/3 plus 1/3 e to the t raised to the power 4. 1. Name this distribution. 2. Find probability that x equals 5. 3. Approximate. Probability that absolute value of x minus 2/3 is larger than what? So answer is 1. What it? Pardon? Fine. With parameters? The first parameter is always n, the second the probability. Huh? And the first parameter is always n. 4. And p 2/3. That's how you can see from that x follows binomial with n equal 4 and p equals 2/3. Second question, what is probability that x equal 5? Huh? Why? N is 4, and what links N to 5, which makes it 0?
Which is equal to formula.
That's exactly what you need to say.
Yeah.
The density, the probability mass function is non-zero for what values of K? 0, 1, 2, 3, 4. 5 is none of that, so the probability that X equals 5 is 0 because 5 is not in the range of the variable. So, and usually there are some really funny things like that that shows up in the work when you start thinking, how do I handle this? But it's just that it's not supposed to be there. Now, what's the third question? Approximate this. How do you approximate this? You put larger than or equal to avoid people having issues, right? So, how do we approximate this? Make it easier.
Solve this inequality and look for some
So carefully. What does it look like? Chebyshev. So that Chebyshev's inequality, that the form of it that you need to look for. You need to look for what this is in terms of sigma square of the distribution and approximate the thing as 1 over k squared, right? Finding the k. So here, we need to think of Chebyshev's inequality. What's supposed to be here in Chebyshev's inequality? Huh? Should be k times sigma. So you want to see k sigma equals 1/4. What is sigma? You got to find that first, and then that's what you give. It's going to give you a k. What is sigma here? In this case, sigma squared equal what? I was given in the previous slide. What's sigma squared for binomial? Variance. And p times 1 minus p. So, and what is p? That's 4 1/3, 2/3. That's 8/9. That's sigma square. You need sigma. So sigma is 2√2/3. And so you have k times 2√2/3 or 1/4. To solve to get k equals 3 over 8/2. So technically, that's what you have to do. And that's going to tell you that this is less than answer. 1/k². And in this specific case, it is useless. Because that's too small a number. Okay. The values here are 1, 2, 3, 4, and you're comparing the difference to 1, 4. Too small. That's why the upper bound that you get here is a number that is even larger than 1, so it's useless. All right, that's it for today. Any questions? If you don't have any questions, I will be happy to see you next time.